This is a masterpiece of modern technology, a device more powerful than the supercomputers of a bygone era, resting in the palm of your hand. But its origin story is one of controlled chaos.
Welcome to the future. Welcome to the new Samsung Galaxy S.
According to industry data, Samsung ships over 250 million smartphones every year. That's nearly 8 phones every second. Each one houses a processor more complex than early spacecraft. Inside the factory, thousands of robots and technicians move in a flawless, synchronized rhythm. Here, the greatest enemy is a margin of error invisible to the human eye. A misalignment of just 0.03 millimeters, thinner than a human hair, is enough to doom a device worth hundreds of dollars to the scrap pile in an instant. So, how is a Samsung smartphone truly born? Samsung's story began in 1938 in South Korea, not with electronics, but with trading dried fish and noodles. Decades later, the company entered the electronics market, producing black and white TVs in the 1970s. By the early 2000s, Samsung had already become a leader in display and semiconductor technology. In 2009, it launched the first Galaxy smartphone, introducing sleek design and advanced mobile chips that rivaled Apple's iPhone. Within a few years, Samsung transformed from a regional brand into a global tech powerhouse. Today, more than 1.5 billion Galaxy phones have been sold worldwide, making it one of the most recognized names in modern technology. Behind each model is a long history of precision engineering and innovation built inside massive high-tech factories. But what does it actually look like when a Samsung smartphone takes shape from raw materials? Let's take a closer look inside the factory. Every Samsung smartphone begins long before the factory line starts moving. Engineers design every detail using advanced 3D modeling software, from the curved glass to the position of each screw. The components come from multiple Samsung divisions. OLED screens are built in Samsung display plants, while processors and memory chips are made in its semiconductor fabs. Camera modules, frames, and batteries arrive from certified suppliers across Asia. Each piece is labeled with barcodes and stored in anti-static trays to prevent damage. Even a single dust particle can ruin a microchip worth hundreds of dollars. Every component is inspected, scanned, and logged for traceability before entering assembly. Nothing goes unrecorded in this process. It is precision planning on a massive scale. But how do these thousands of tiny parts come together to form the phone's electronic heart? Inside a clean room, workers wear white protective suits to keep out dust. Here, the phone's brain takes shape. A stencil printer spreads a thin layer of solder paste on a green PCB panel. Then, robotic arms called pick-and-place machines position thousands of micro-components at lightning speed. Each robot can place over 30,000 parts per hour, moving faster than the human eye can follow. Once all parts are in place, the board passes through a reflow oven heated to about 250 degrees Celsius, melting the solder and locking everything in place. Automated optical inspection cameras then check alignment down to microns. A single misplaced chip is flagged for correction. The result is a perfectly built circuit board ready to control every function of the phone. So, what happens once the electronic brain is complete? Now the heart meets its body. The main frame, made from aluminum or reinforced polycarbonate, moves along the assembly line. Technicians and robots work side by side to fit the PCB, camera lenses, and connectors into position. The flexible OLED display is then mounted using an alignment machine with 30-micron precision. Any error could make the touchscreen fail later. Adhesive layers and fine connectors are pressed into place by robotic arms. Next, the lithium-ion battery is installed and linked to the mainboard. Each battery has already passed safety tests for heat, pressure, and puncture resistance. Finally, the camera module, speaker, and vibration motor are attached. The phone now looks complete but still lifeless. This is where the phone comes alive. Hundreds of devices are connected to an automated flashing system that installs Samsung's One UI software in seconds. The firmware, apps, and security updates are loaded simultaneously. Then, each phone moves through a series of tests. Cameras capture sample images to check focus and color. Touchscreens are tapped by robotic fingers to verify accuracy. Speakers, microphones, and sensors are tested for sound clarity and response. Inside radio frequency chambers, antennas are measured for signal strength and stability. Every function must pass before approval. Fun fact: Samsung phones undergo over 350 automated tests before packaging. Each result is stored in a central database for quality tracking. So, what does the final stage look like before these phones reach the store shelves? At this stage, finishing touches turn each unit into a consumer-ready product. Robots attach the glass back cover using precision adhesive dispensers. Pressure machines seal the edges to create water resistance that meets the IP68 standard. Camera lenses, fingerprint sensors, and Samsung logos are carefully added. Then comes the quality inspection. High-resolution cameras detect dust, scratches, or misaligned parts. Random phones are dropped, bent, and exposed to mist inside sealed chambers to test durability. Only units that pass every test continue forward. Those that fail are either reworked or recycled. The assembly line glows under bright lights as phones move toward packaging. What happens next decides how they travel from this spotless room to millions of hands around the world. Once approved, the phones are powered off and cleaned with anti-static air. Each one is paired with its accessories, charging cable, SIM tool, and user guide. Automated machines pack them into Samsung-branded boxes, seal them, and attach regional labels. Every serial number is scanned for digital tracking. Boxes are then grouped by model and destination, loaded onto pallets, and sent to Samsung's global logistics centers. From there, they're shipped to stores and online retailers across the world. Every phone's journey can be traced from the production line to the customer's hand. After weeks of engineering and testing, the process ends where it began, in human hands, pressing the power button for the very first time. According to IDC, over 420 million computer keyboards are sold every year worldwide. That's more than 1 million units every single day. From office desks to gaming setups, these devices connect people to technology with every click. Yet behind each key you press lies a surprisingly complex process. It involves molten plastic, steel molds weighing hundreds of pounds, and robotic arms placing keycaps with perfect accuracy. Every sound you hear while typing begins here, inside massive factories where design meets precision. So how does a pile of tiny plastic pellets turn into the keyboard sitting in front of you right now? Let's step inside and find out. The story of the modern keyboard began long before computers existed. In the late 1800s, typewriters became the first machines that turned human thought into printed words. The famous QWERTY layout, created in 1873, was designed to prevent typewriter keys from jamming. When computers arrived in the 1970s, engineers adapted this layout for electronic input devices. In 1984, IBM released the Model M keyboard, known for its spring-loaded switches and loud click that many users still love today. As technology advanced, plastic replaced metal, and mass production became faster and cheaper. Mechanical, membrane, and wireless keyboards now fill homes, offices, and gaming setups worldwide. Yet the essential goal remains the same: to convert touch into data. From the heavy typewriters of the past to today's silent keys, this evolution reveals one truth: precision still defines every keystroke. But how do factories build millions of these devices with such accuracy? Every keyboard starts with a design file. Engineers use CAD software to map every detail, from the outer frame to the internal key layout. Each curve, screw hole, and switch position is digitally tested for strength and comfort. Once approved, the design data is sent to a machine shop where heavy steel molds are built. These molds, often weighing more than 500 pounds, are carved with micron-level accuracy using CNC milling machines. Each mold can produce tens of thousands of identical parts without losing precision. Workers polish the cavities to a mirror finish, ensuring every key will fit perfectly. Creating a single mold may take several weeks, but it defines the shape of every keyboard that follows. So, once the molds are ready, how do factories transform small plastic pellets into those solid frames and keycaps? In the molding area, the sound of machinery fills the air. Large injection molding machines melt plastic pellets at around 200 degrees Celsius, 392 degrees Fahrenheit. The molten plastic is then injected into the steel molds under high pressure. Inside each mold, the liquid plastic fills every cavity to form the keyboard's base, frame, and keycaps. Within seconds, the plastic cools and hardens into shape. Robotic arms open the molds and remove the finished pieces with precision. Each part slides onto a moving conveyor belt and is air-cooled before trimming. Any excess edges, called flash, are cut away using automated blades. The result is a set of smooth, clean components ready for printing. The faint smell of warm plastic lingers in the room as rows of molded keys roll forward. But how do those blank pieces become the familiar letters and symbols we see every day? This is where each blank key gains its identity. Most factories use pad printing or laser etching to add letters, numbers, and symbols. In pad printing, silicone pads pick up ink from etched plates and stamp it onto each keycap. A single machine can print hundreds of keys in a minute. For backlit keyboards, manufacturers use laser etching. Here, a laser burns off a thin surface layer, leaving translucent letters that glow when illuminated. Some high-end models use double-shot molding, where two layers of plastic fuse together to create characters that never fade. After printing, the ink is cured under UV light to prevent smudging. Quality control cameras inspect each key to ensure perfect alignment and sharpness. Any defect, even slightly off-center text, is rejected. With all keys now labeled, the next step is to give them life through circuitry. Inside the assembly hall, the true function of the keyboard begins to take shape. For membrane keyboards, thin plastic sheets are printed with conductive ink to form electrical paths. When pressed, the top sheet touches the bottom one, completing a circuit. For mechanical keyboards, it's a different story. Each key uses an individual switch made of springs and metal contacts. These switches are either assembled by robots or soldered onto a PCB. Different switch types create different feels. Linear for smooth typing, tactile for feedback, and clicky for sound. Workers test each row to confirm signal accuracy before adding a microcontroller chip that processes keystrokes. This small chip translates every press into digital data. It's the unseen heart of your keyboard. But how do these circuits and key switches become the solid device you can actually type on? On the production line, parts begin to come together. The circuit board is fitted into the lower plastic frame, and the top cover is secured using tiny screws or snap-fit joints. Next, the pre-printed keycaps are carefully pressed onto the switches. Automated arms perform this with near-perfect accuracy, pressing dozens of keys at once. Once assembled, every keyboard goes through testing. Robotic fingers tap each key to ensure it responds correctly. LED lights are turned on to verify color and brightness. Wireless models are paired via Bluetooth to check connectivity and latency. Any product that fails these tests is sent for repair or recycling. The rhythmic tapping of hundreds of robotic fingers echoes through the factory, a sound that mirrors the millions of keystrokes these keyboards will one day endure. So, what happens before these finished keyboards reach your desk? Once approved, the keyboards are cleaned and packaged. Each unit is wrapped in protective film, then placed in a cardboard box with manuals, cables, and sometimes a wrist rest. Automated packaging lines fold, label, and seal the boxes within seconds. Barcodes and serial numbers are scanned into the system for tracking. Workers stack the boxes into larger cartons, which are shrink-wrapped and placed on pallets. These pallets move to the warehouse, where logistics teams arrange shipments for global delivery. Some keyboards head to tech retailers in the US, while others travel across the world to online customers. Every product can be traced back to the exact production batch that made it. From raw pellets to the sound of your typing, each keyboard carries a story of precision, repetition, and design. Born in the factory, finished at your fingertips. Every day, more than 120 million electric toothbrushes hum to life around the world. Each one performs over 30,000 movements per minute, scrubbing away plaque with the precision of a tiny machine. But behind that quick 2-minute routine lies an impressive piece of engineering. Inside its sleek handle are powerful motors, waterproof seals, and microchips that rival those used in smartphones. From the melting of plastic pellets to the final waterproof test, every step is a story of precision and design. Today, we'll go inside the factory to see how electric toothbrushes are made, step by step. The story of the electric toothbrush began in Switzerland in 1954, when Dr. Philippe Guy Woog created the first model to help patients with limited mobility clean their teeth more effectively. Early versions were large, noisy, and needed to be plugged into the wall. In the 1960s, American brands improved the design, adding safer, low-voltage power systems. By the 1980s, rechargeable batteries and smaller motors made them portable and affordable for homes worldwide. Modern versions use lithium-ion batteries and microchip control, allowing up to 62,000 brush movements per minute. Some even connect to smartphones to track brushing habits. From a simple medical aid to a precision device found in millions of bathrooms, the electric toothbrush has become a symbol of how everyday objects can evolve through technology. So, how does this tiny device come to life inside a factory filled with heat, motion, and precision? Every electric toothbrush begins with precision design. Engineers use 3D modeling software to shape the handle, motor housing, and detachable brush head. Each part must fit perfectly to stay waterproof while protecting delicate electronics. Suppliers then produce the main components: durable ABS, or polypropylene plastic for the body, tiny DC motors that spin at over 8,000 revolutions per minute, and rechargeable lithium-ion batteries that can last for 2 weeks on a single charge. Printed circuit boards, or PCBs, are designed to control motor speed, pressure sensors, and smart timers. Before entering the assembly line, every shipment is tested for strength, power, and size accuracy. Technicians inspect samples under microscopes, checking for tiny defects invisible to the eye. Once approved, these parts move to the molding section, where molten plastic will take shape as the toothbrush's outer shell. But how do they transform raw plastic pellets into a sleek, solid handle ready for the electronics inside? Plastic pellets arrive in large silos and are vacuum-fed into molding machines. Inside each machine, the pellets heat up to over 400 degrees Fahrenheit, 200 degrees Celsius, until they melt into a thick, glossy liquid. This molten plastic is injected into precision steel molds that shape the handle, base, and brush head casing. The molds cool in seconds, locking the plastic into solid form. Robotic arms lift the fresh shells and place them onto conveyor belts. Workers trim off thin excess edges known as flash and inspect every piece for smooth surfaces. Some handles receive a second layer called a soft grip overmold, made from flexible rubber to improve comfort and reduce slipping. Logos and model codes are laser-etched for permanent marking. After this step, thousands of perfectly shaped shells roll down the line each hour. The body is now ready to house the motor, battery, and electronics that bring the toothbrush to life. So, what happens when these empty shells meet the powerful core inside? At the next station, machines and technicians begin building the toothbrush's heart. The small DC motor is fitted into the lower body and connected to a thin metal shaft. This shaft transfers motion upward to the brush head, turning rapid rotations into gentle vibrations. Depending on the model, the gearbox converts spinning motion into oscillation or sonic vibration, up to 62,000 micro-movements per minute. The battery is welded directly to the PCB, which manages power flow and automatic shutoff after 2 minutes. Tiny sensors detect pressure, warning users if they brush too hard. Every wire is placed with precision to keep the inside compact and waterproof. The two halves of the body are sealed using ultrasonic welding, a technique that fuses plastic with high-frequency vibration instead of glue or screws. This makes the toothbrush completely watertight. With the motor sealed and tested, attention now shifts to the part that touches your teeth, the brush head. But how do factories produce millions of tiny, perfectly arranged bristles so quickly? In a separate section of the factory, injection molding machines form the brush head base. Here, fully automated tufting machines take over. They work at incredible speed, inserting up to 1,000 nylon bristle bundles per minute. Each bristle is fed through a metal tube, cut to length, and heat-sealed into place. Different designs require different patterns. Some heads have angled bristles for better reach. Others combine soft and firm nylon for polishing and deep cleaning. Once tufting is complete, The brush heads are polished to remove sharp ends and then cleaned with warm air. To ensure hygiene, they pass through UV sterilizers or ozone chambers that eliminate bacteria. Finally, a metal connector or snap-on base is added, allowing easy attachment to the handle. Workers test how firmly each head locks into place. When the head fits securely, the toothbrush is nearly complete. So, how do factories make sure each brush performs perfectly before it reaches your sink? Every finished toothbrush goes through strict testing. Automated machines check motor vibration, rotation speed, and power output. Each battery is charged, discharged, and tested to confirm performance over 300 cycles. To verify waterproofing, toothbrushes are submerged in water tanks and sprayed under pressure. If even a single air bubble escapes, the unit fails. Durability machines press the bristles against simulated teeth thousands of times to check for wear. Only the best units move to final cleaning and packaging. Here, each toothbrush receives its charging base, brush head, and user guide. Packaging lines fold boxes, insert components, and seal them in plastic wrap. High-end versions include travel cases or USB chargers. Every box gets a barcode for tracking before being packed into cartons and stacked onto pallets. Within hours, pallets leave for distribution centers worldwide. From raw plastic to a high-tech hygiene tool, each toothbrush completes its journey through precision, motion, and quiet innovation. From the smartphone in your hand to the keyboard beneath your fingers, and even the toothbrush by your sink, each of these everyday items carries a story of precision, design, and invisible craftsmanship. Inside every Samsung factory, molten metals and microchips form the heartbeat of modern communication. In keyboard plants, streams of plastic and laser-etched letters connect our thoughts to machines. And in toothbrush lines, nylon fibers and high-speed robots build the simplest tool that keeps us healthy every day. These factories don't just build products, they build habits, memories, and the rhythm of daily life. Behind every ordinary object lies an extraordinary system of human skill and machine perfection. The next time you text, type, or brush your teeth, take a second to imagine the world of engineering that made it possible. If you enjoyed discovering how these common products come to life, hit like, share this video, and subscribe to Captain Discovery for more journeys inside the world's most fascinating factories.